It doesn't take much aeronautical knowledge to understand that, when an aircraft takes off, it needs to ascend at a minimum rate of climb, angle, or gradient, that allows it to overfly the obstacles that may be present in its flight path. Airports are normally built in flat areas, so that normally operating aircraft can comply with this limitation, most of the time. However, aircraft may suffer an engine failure during this takeoff phase. In this case, it is possible that the rate of climb attainable with one engine inoperative, it's not sufficient to clear all obstacles, and this has to be taken into account when planning a flight. Here, we need to talk about the importance of a good runway analysis. It will determine the maximum takeoff weight, taking into account the temperature, runway length, contaminants such as snow or water, with which the aircraft can take off, and expecting an engine failure at the most critical point, that is, just after V1, or the point at which the aircraft cannot reject the takeoff. Airlines, and operators of large fleets, usually perform this analysis in-house, with the aid of specially trained dispatchers and software. But many operators may outsource this task to specialized companies, since it's not always an easy task. The main advantage of a good runway analysis is that it will optimize the takeoff weight, thus allowing to take more passengers, cargo or fuel. Runway analysis studies the obstacles along the normal takeoff procedures, or SIDs. In many cases, these studies may also add special departure procedures, to be flown in case of an engine failure instead of the normal SID. These routes, often called EOSIDs, or EFPs, are drawn over easier terrain, and allow for a higher takeoff weight. At one point, both routes, the SID and the EFP, will separate, and we call this point the deviation point, or diversion point, DP for short. In this case, the EFP may say something like, in case of an engine failure, turn left direct to a certain VOR, and ascend there in a holding pattern, etc. Let's see this in a normal departure chart. Red dots mean obstacles. The intended path is green, but in case of an engine failure over the runway or shortly after, we need to turn left, so as to intercept and proceed over the 090 radial of Victor Romeo Alpha VOR, direct to Papa November VOR. All this is very well, and it's the basic explanation of obstacle clearance on takeoff. But now the fun starts. If an engine fails over the runway or close to its end, we will turn left. If not, we will proceed to Victor Romeo Alpha VOR and continue on the green path. The question is, what happens if the engine quits after we have already passed the DP? Are we sure that we can turn left and fly the EFP? We can also continue the SID, but are we sure that we can clear all obstacles along the intended SID with a crippled aircraft? The FAA has always said that if the engine fails after the DP, then you will have to improvise. Use your charts, the terrain proximity warning system, or look through the windows. In other words, use common sense. It will all depend on the altitude the aircraft has already attained, and there is no way we can contemplate all scenarios since we don't know when the engine will fail, if ever. But everybody knows that in Europe we are very clever, and the European Union Aviation Safety Agency introduced an acceptable means of compliance that, in my humble opinion, is totally wrong. Not only wrong, but dangerous, which is not bad for a safety agency. If compliance with CAT-POLA 210 is based on an engine failure route, that differs from the all-engine departure route, or SID normal departure, a deviation point can be identified where the engine failure route deviates from the normal departure route. Adequate obstacle clearance, along the normal departure route, with failure of the critical engine at the deviation point, will normally be available. However, in certain situations, the obstacle clearance along the normal departure route may be marginal, and should be checked to ensure that, in case of an engine failure after the deviation point, a flight can safely proceed along the normal departure route. Our concern here is, what is this normal departure route? Everything seems to indicate that this normal departure route is the assigned SID, prior to the engine failure. Imagine you are departing Asturias southbound, and just before entering the high terrain of the Cantabrian Mountains, your right engine fails. Would it be wise to continue into those mountains, instead of just turning north, when you have the low terrain and the Atlantic Ocean, just a few miles away? Don't you think that forgetting the SID, and turning right to a general north direction, would be the right move? Wouldn't you prefer to fight the emergency over the sea, or low terrain, rather than over the peaks of Europe? I certainly would. Of course, I'm thinking of the less powerful twin-engine aircraft. Please bear in mind that an engine failure is not the same in an Airbus 380 or in a small turboprop. Also, that engines may die slowly with plenty of notice, or they can quit suddenly, without a warning, creating a severe asymmetry in some aircraft, on top of the climb problem. Often, by the time the crew regains control of the aircraft, they may find themselves a couple of miles off track. An engine failure is always an emergency, and in an emergency the pilot in command decides what to do. No rules and regulations, no ATC instructions can compel the crew to continue flying towards mountainous terrain with a crippled aircraft. Another question mark is, for how long should the aircraft follow this normal route? SIDs can be very long, and, by definition, they will take you away from the airport. Some SIDs from Barcelona will end at the French border. Do I really want to go that far with my smoking aircraft? The guidance material says nothing about this. Having been so critical with the European rule, now, I have to agree with one thing. Yes, although in many airports losing an engine after the DP will not pose a problem, there are airports where an engine failure procedure is not enough. Geneva, or Zurich, for example, require a far more serious analysis. A few years ago, we came up with a procedure that allows us to comply with this European requirement, and we developed a software that projects the terrain, on top of standard SID charts, as you can see in this example. We use SRTM1 and 3, to which we can add published obstacles. Our software can project either a flat surface, or a cone, from this point, with the gradient we want, both positive or negative, and see whether there is any interference with the terrain and obstacles. We can establish a minimum net gradient with one engine inoperative, let's say 1 or 2%, that everyone will agree we can attain under the most extreme conditions, and use it instead of a flat disk, in order to identify obstacles that could pierce through this conic surface. But before we show you this with more detail, let me explain the basic concept of these analyses. As mentioned before, the key parameter is the altitude at which the aircraft will reach the DP, with all engines running normally. This is not always an easy task, because the manuals contain more data for one engine inoperative than for both engines running. Anyway, from the AFM and the operation manual we can get a fairly accurate idea of how much runway a particular aircraft will use before reaching 50 feet, at maximum takeoff weight, and let's say 40 degrees Celsius, 0 wind, and 1000 feet altitude, for Europe. We can also figure out a net gradient with both engines at maximum continuous thrust. For most of corporate aircraft this should be some 7% net gradient. Probably it's much more, but what we want is a very conservative figure that nobody can dispute. With these parameters we will obtain the altitude at the departure end of runway and with a simple calculation, at the DP. Now, with the aircraft positioned at this point in space, we can find just a few scenarios. Case 1 is that the aircraft is already clear of all obstacles within a radius of, let's say, 25 nautical miles from this point. In my opinion this distance is enough to maneuver the aircraft back to the airport of origin or another airport close by. As explained before, we don't want to fly forever with an ascendability challenged aircraft. Case 2 is a situation where the cone interferes with terrain at some areas, but the trajectories of SIDs are not affected. This is better seen from a vertical point of view. In this case, you can safely proceed along the trajectory of any SID with a minimum climb gradient of a 1%. Again, the trajectory must not be too close to obstacles. We don't want to design an exact escape route down to a few feet accuracy. We don't want precision, but rather peace of mind. Case 3 is when the trajectories of SIDs are affected by terrain, using this conic analysis, but there are better strategies, in case of an engine failure, than just following the SID. This is the case we have seen before. The DP is very close to the runway end, but if all goes well, the aircraft will have attained, by 7.7 dme, enough altitude to continue the rest of the SIDs with a 1% gradient. What we need to tell the pilot in command is that in case of an engine failure before reaching 7.7 dme, he must turn north immediately. After this point, the aircraft can continue any SID. But I wonder who would do this. Why? Why? In only a few airports, we may be compelled to calculate with more precision the trajectory of an SID, and determine the minimum gradient necessary for obstacle clearance. Please be aware that many SIDs will publish a minimum gradient, but this is not always because of obstacles. Most of the time it's just traffic control convenience, but in case of an engine failure, you will not be subject to this limitation. Also, that SID gradients are calculated starting at 35 feet above the departure end of runway, but if all engines are running, the aircraft will be much higher than that. In this case, we will find the DP and the altitude at this point, as explained before. But, instead of projecting a cone or a circle, this time we will draw a tangent to the vertical profile of the trajectory of the SID, plus the regulatory margin. This will give us the minimum gradient required for this particular SID. Then, the crew will decide whether the aircraft can safely fly the SID with the actual weight and temperature. We can obtain the profile of the SID by clicking its points from a calibrated map, and then calculate the maximum altitudes of this track, with the width and shape of the ICAO standards, and present it in a graphic mode. I'm sorry I cannot show you how we do this, because, for some reason, the cursor disappears when I record my screen, but at least you can see that we can draw a fine line over the SID trajectory, and create a table with the coordinates of each point. I am in favor of using very safe margins for weight, temperature and net gradient, so that we can apply this paragraph at categorization stage, and forget about this airport. But, of course, we can use exact data from the AFM and perform a very accurate analysis whenever necessary. Thank you for listening to this boring presentation, but I'm sure that it will be useful for someone out there.